Welcome to Ready to Derive. In this video, we get to derive, no surprise there, the power rule, which is going to be your best friend moving forward in calculus. This shortcut for finding the derivative of a power function will save you from all those tedious limit calculations that have filled the pages of your calculus notebook thus far. And if you're curious as to how Pascal's triangle could have anything to do with derivatives, keep watching as you're in for a treat. And if you have never seen or heard of Pascal's triangle, also keep watching, as you're in for a double treat. So without further ado, let's get started. So let's begin by defining what exactly a power function is. A power function is any function that can be written in the form f of x equals x to the n, with the condition that n is a real number. So let's look at some examples and take them one by one. So x to the 10, that's pretty clearly a power function. 10 is a real number and the variable is in the base. Now this one may not look like a power function at first, because you might just say, well, that's a radical function, but if you rewrite it as x to the 1/3, we get it in the form x to the n. 1/3 is a real number, check. Now you might notice there's a power function in the denominator here with 1 over x cubed, but with the power function, as you can see up here, x has to be in the numerator. So we need to rewrite this as x to the -3 and check, that's a real number. Now x, well, if you realize that that's really just x to the first power, now that's a power function, check. X to the pi is a real number. It's irrational, but that's still real, check. And then finally, a more complex radical expression can be rewritten as x to the 5/2, check. Now, so let's look at some functions that are not power ones. So let's reverse. Instead of x to the 10, if we have 10 to the x, we have an exponential function. That is not the same as a power function. The variable must be in the base, the number in the exponent. Absolute value of x can't really be written as x to the n. Now, technically, if you write it as a piecewise function, you could express it in terms as a piecewise function of two power functions, but not as it stands, just like that. Ln x is clearly not a candidate. Cosine x, again, none of these can be written in the form x to the n. You might think with something like 1 over 1 plus x, you might say, well, isn't that the same as 1 plus x to the -1? But the problem is 1 plus x as the base is not permissible. It has to be x to the n. And finally, another exponential function, e to the x. Again, the variable is in the exponent and the number is in the base. So that is not a power function. So at this point, having defined a power function, I could have just stated the power rule and done a few practice problems and be done with it. But I can't. As the title of my YouTube channel suggests, Ready to Derive, I can't miss an opportunity to show you a really exquisite derivation. And it all begins with Pascal's triangle. And this may seem like a diversion, but it's actually, very essential to understand how the power rule works. And it's also a beautiful pattern. So this is named after the 17th century French mathematician Blaise Pascal, but there is evidence that it was known as far back as the 11th century. And let's get started. So the very first element of Pascal's triangle is 1. The next is 1, 1. And if I asked you to predict the next row, you'd probably be like, well, 1, 1, 1, because you haven't got enough to go on. But I'm going to give you the next row and the row afterwards. All right, and the rows are categorized. So this is considered the third row, the second above, the first, and of course, then this is the 0th row. So let's just put those in there so we can refer. So maybe pause the video a moment to figure out if you can predict the 4th row. And here it is. So if you didn't or hadn't picked this up, what the pattern is that to get there's ones along the left side, ones along the right side of the triangle, and to get every other term, you add the two terms above. So 1 plus 1 is 2, 1 plus 2 is 3, same here. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So that's how Pascal triangle, how it's developed. And the really important thing to know, there's so many beautiful patterns in this triangle, but the most important thing to do is to understand what these, I'm going to call them coefficients, you'll understand why in the next slide, what these numbers 1, 4, 6, 4, 1, what they actually represent and why they matter in real life. So I want you to think about 4 people. So I have 4 people, and I would like to choose one person from that group of 4, maybe for like the president of a club. So this number 4 here, let me just make this connection. 4 is the number of ways of choosing one person from a group of 4. I could choose person 1 as my president, person 2, person 3, and person 4. Now, what about though if I wanted to choose 2 people from the group of 4? So that means I might want to choose co-chairs. So I'm groups of 2 from 4, and I'm going to tell you right now that that is the number 6. So let's have a look at it over here. So if I'm going to have my groups of 2, I could have person 1 with person 2. That's one set of co-chairs. Person 1 with person 3, person 1 with person 4. I've now considered all groups, all pairs with person 1 in it, so they're kind of out of the count right now. So right now I've got 3. Then person 2 could go with person 3 or person 4, and then person 2's out of the picture, and then the last grouping could be person 3 with person 4. And if you count those up, that works out to be 6. So these coefficients, each row of Pascal's triangle gives some coefficients that are really useful in the mathematical topic of combinatorics and will be useful for us in the next slide. So in this slide, we're going to be doing some algebraic manipulation that maybe feels a little unrelated to Pascal's triangle and also to the big picture of this video, which is the power rule. But there's a method to the madness, so bear with me. I'd like you to first expand x plus h squared by multiplying x plus h times x plus h. That should look familiar to you. It's x squared plus 2xh plus h squared. I'd like you to do the same with x plus h cubed. Now that would entail taking this and multiplying by x plus h, and a lot of distributing, a lot of combining like terms, and maybe pause the video for a moment just to try that yourself to see if you come out with this. So, of course, I'm going to ask you to do x plus h to the 4th now. And about at this moment, you should be getting a little frustrated because to multiply the expression before by x plus h is going to be a lot of distributing, a lot of combining like terms. So instead, I'm going to ask you to, we're going to note some patterns here. So notice that whatever you are raising x plus h to, that is going to be, the first term is always going to be x to that power. So this was cubed, so it was x cubed. Then notice that the powers of x start decreasing for every term. So 3, 2, 1, and the last we would have x to the 0. And in contrast, the powers of h are increasing, h to the 1, so h to the 2, and h cubed. There's some wonderful symmetry here. So take a moment to see if you could predict at least what the terms are for the x plus h to the 4th. And then we'll worry about the numbers in a moment that go in front of the terms. So you start with x to the 4th, and then x will drop down a degree, x cubed, and h will start building up. And the pattern should look familiar and very symmetrical. Now the problem is, without doing all the multiplying out and combining like terms, we're not sure of the coefficients that would go in front of those terms. Or are we? Take a look up here. Notice that the coefficients here are 1, 2, 1. That should look familiar, right? The second row of Pascal's triangle. And then the next one, 1, 3, 3, 1, 1, 3, 3, 1. And so it wouldn't be hard to predict the next row. That row of Pascal's triangle is going to form the binomial, what are called the binomial coefficients of the expanded form. Now, as in the last slide, it's kind of helpful to understand, well, what does that number 4 mean? What does that number 6 mean? Well, once again, remember we described how the 4 was the number of ways of choosing one item from 4. Well, that's the same as saying the number of ways of choosing 1h and 3 x's. That's how I get x cubed h. And the way to think about this is to think, well, in what ways can I get x cubed h? If I label each binomial with a different index, so x1 plus h1, etc. And the ways to get x cubed h, you can see, well, I could take x1 times x2 times x3 and then use the h4 from the fourth parentheses. So I could get that. That's one way to get x cubed h. But I could also have picked the h from the third parentheses and the x from the fourth, etc., etc. So in effect, there are 4 ways of getting at x cubed h. And then, not surprisingly, this number here, the 6, is the number of ways of choosing 2 h's and 2 x's. We won't go into that right now, but you could certainly make a list like I did to verify that there's 6 possible ways in which that could happen. So now the fun begins. Well, at least I think it's fun. I hope you do as well. We're going to find the derivatives of x squared and x cubed, both power functions. Admittedly, we're bypassing x to the first power, but that's such an easy calculation to do that it's not worth it. It's better to start with these, and we'll revisit x to the first power. So we're going to use this definition of the derivative. Now, hopefully you're seeing why we were expanding x plus h to various powers in the previous slide. And let's start with f of x equals x squared. So by that definition, we will have to work out this limit. And notice that f of x plus h, of course, is x plus h squared. So we draw on what we did in the last slide and we expand that. And we note that the x squared terms cancel. And then we are left with 2 terms that have a common factor of h. I'm going to factor that out right now. And observe that the h's cancel. And then also observe that as I can at a stage where I can legally plug in h equals 0. So this term will go to 0. And then we get that the derivative of x squared is 2x. Let's repeat for f of x equals x cubed. Here is the definition of the derivative, x plus h cubed. How convenient, again, that we worked that out in the previous slide, thanks to Pascal's triangle as well. So let's expand that out. And once again, we observe that the x cubes cancel. And we are left with 3 terms, all of which have a common factor of h. So I am going to take out that factor of h. I'll left with h squared here. Cancel the h. Once again, it's safe now to plug in h equals 0. That will send this to 0 and this to 0. And we get left with the derivative of x cubed is 3x squared. So we're sailing along. So let's do one more example, the derivative of x to the 4th. Since we had expanded this using Pascal's triangle, why not use it? So we are going to evaluate this limit, which means expanding x plus h to the 4th, which you will recall was this long expression. Now notice the x to the 4th cancels, so that's convenient. X to the 4th cancels, and we are left with an expression in the numerator where the only common factor is h. So let's factor that out. 6x squared h plus 4xh squared plus h cubed. The great thing about being able to factor out that h is it cancels, making it possible to plug in h equals 0. And notice that every term after the first one, goes to 0. Leaving us with what stands alone is that 4x cubed, and therefore the derivative of x to the 4th is 4x cubed. So let's recap where we've got to so far. So in terms of developing the power rule, let us see that for when f of x was x squared, the derivative is 2x. For x cubed, it was 3x squared. and x to the fourth, it was 4x cubed. Now maybe you can make an inference. Try and stop for a moment and think about what the derivative might look like if it was x to the n. And if you notice, so for example, up here, that 2 dropped down in front. Here, the 3 dropped down in front, and the 4 as well. But a little more is happening at the same time. Notice that it's obvious here that the exponent drops by 1. And that's even true up here. So the formalization of that is that if f of x equals x to the n, we're pretty confident that f prime x will equal nx to the n minus 1. Once again, where n is a real number. Let's go about proving the power rule for the general case f of x equals x to the n. So if we call up the limit definition of the derivative, we realize that we actually, having to expand x plus h to the n is going to be challenging. We know the first term is x to the n. And we know from Pascal's triangle, well, what do we know? We know that the nth row the first number will be 1, the second will be n, but finding the third number is actually going to be challenging because we don't have the rows above it. So I know that we can get the first term, the first coefficient is n, x to the n minus 1, and then we pick up an h. And then I'm not sure what that number will be. I'm just going to put number there. I know that then the x degree will go down 1 and we'll pick up another factor of h. And I'm going to tell you that what happens after this point, what happens after here, doesn't really matter what those terms are, as you'll see shortly. And we do know that the very last term will be h to the n. So let's work with that. I'm going to expand it, and I'm going to say to you that keep an eye on from this point to this point, what happens in the next step. So once again, x to the n cancels, and we are left with an expression, a very long expression in the numerator. But notice that all the terms, even the first term, has a common factor of h. So we're going to pull that h out. We're left with this. And then we have the number that we're not sure what it is, but whatever that number is, we know that then we would have x to the n minus 2 with one factor of h plus, and every term after this will still have a factor of h in, and the last will be h to the n minus 1. Once again, conveniently, the h's cancel, and I'm at a stage where I can plug in h equals 0. Well, now you'll see why we never had to work out what that number was, because this term will go to 0, and every term afterwards, right up until here, will all disappear. And then, of course, what are we left with? The power rule, that the derivative of x to the n is n times x to the n minus 1. So we are going to end by finding the derivative of all the examples of power functions we looked at in the first slide. So let's bring them all up here. And some of them are easier than others to work with, but x to the 10 is pretty straightforward. By the power rule, you bring the 10 in front, x, and you lower the exponent by 1, 10x to the 9. Recall that to use the power rule, it really has to be in the form x to the n, so we need to rewrite that as x to the minus 3. Now, so the power rule works even with negative numbers, even with irrational numbers, even with fractions. So we bring the negative 3 in the front, x. Now be careful here, because if you're going to reduce the exponent by 1, it's actually going to be negative 3x to the minus 4, which you should recognize could be rewritten as negative 3 over x to the 4th. X to the pi is a real number, drop the pi in front, x, and lower the exponent by 1. Cube root of x, again, we've got to do a little work here. We have to first of all rewrite it in the form x to the n, and then we take the 1/3 in front and subtract 1 from the exponent. So it's 1/3 x to the, well, 1/3 minus 1 is minus 2/3. Now, if you are expected to turn it back into a radical, it might be good to take care of the negative exponent by writing it like that. And then the third means the cube root. So it's 1 over 3, not to be confused with the cube root of x squared. And that's, well, there's a lot of work there, but that's the final answer. Now, here is x to the first. So what happens there? So we get 1x to the 1 minus 1, which is x to the 0, 1x to the 0, which is just 1. And finally, x to the square root of x to the fifth is x to the 5 halves, and that will be 5 halves, x to the 5 halves minus 1, which is 5 halves, x to the 3 halves, and I'll just leave it like that. You could put it sort of back into radical form if you like to, but we'll end there. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.